Alright, last time we talked about fundamental units of measure, and we said that they were mass, length, and time. These are measured in SI units, or international standards, which mass is kilogram, length is meter, and time is seconds. So, we talked about these in terms of referring to them as fundamental units, but I never really explained why, and I just realized that, so we're going to go over why these are called fundamental units of measure. And the reason is in theory, these are the same everywhere in the universe. In other words, the mass of something, which is ultimately the matter it's made up of, how many atoms it's made up of, will be the same on the moon, let's say, as it is on the Earth, where the length of an iron rod would, again, be the same on the moon as it is on the Earth, and the moon just being an example of some other place in space-time outside of our celestial body of Earth. So time, in theory, again, for classical physics, is the same wherever we're at. So, how do we calculate something outside of the fundamental units of measure? We do something called derived, and I want to make sure I spell this right. Derived, D-E-R-I-V-E-D, derived units. So derived units, so an example of a derived unit we talked about last time was force. Force equals newtons. Newtons are equal to mass times acceleration. Okay? We can also talk about velocity. That's also a derived unit because velocity is not in this list right here. So velocity is equal to meter per second, distance per time. So we see that this derived unit is made up of 2 of the fundamental units. Mass times acceleration. Well, let's factor this out by units. So mass is a kilogram. It's multiplied against acceleration. Acceleration is a rate of velocity, much like velocity is a rate of meters over time. Acceleration is a rate of velocity over time. So a change in velocity. So as that velocity goes faster or slower, as it changes, that is acceleration. So that is meters per second squared, or as I like to say, meters per second. I feel like that is a little simpler. So again, we see, here's 3. Let's call this 3. Here is 1, and here is 2. So we have all 3 units of measure in force, which is equal to newtons. So let's see. Let's clear this out now. So these are called derived units. All right. So let's do one more example of a derived unit. We're going to say weight. Okay. So weight, as we know, changes when we get to the moon, right? Because we see the astronauts bouncing up and down on the moon effortlessly. Well, the reason is because the weight on the moon is 1.6 meters, or excuse me, the gravity of the moon, lowercase g, gravity, is equal to an acceleration, right? Gravity is an acceleration of, on the moon, 1.6 meters per second squared. On Earth, gravity is equal, so we'll put sub E and we'll put sub M. So this is the gravity on the moon, or lunar gravity. This is the Earth gravity. It is also an acceleration. It is 9.81. We're going to round it to 10 meters per second squared, or as I like to say, meters per second per second. I think that ends up working better when you're running out the equations, when you're cross-canceling and looking at things. For me, it's simpler. So, and I'm just a simple guy, so I like to keep these things less mysterious, physics and math. In chemistry, keep it less mysterious, but show it for what it is, which is, really quite intuitive. So again, gravity on the Earth is 10 meters per second squared, while gravity on the moon is 1.6 meters per second squared. So when we talked about acceleration as meters per second, right? It's a rate of velocity right here, because, right, velocity equals meters per second. So we see a rate because it's divided by, right? It's a rate of velocity over time right here, right? Because time is equal to seconds. So we see it's v over t, essentially. Or really delta v over t. Delta, this symbol right here, is a Greek symbol called delta, and when we put it in front of a v or anything else, it just means change in. So we're going to take the velocity final, the final velocity of something, we're going to subtract it from the initial velocity, and that would give us the delta velocity. So this is equal to acceleration. Again, if we're going too quick, it's just because we have a limited time to record, so go ahead and rewind, play parts of it, play the whole thing over again. And if you have any questions, always feel free to message me, and I'm going to always do my best to respond to those questions with a video. Not just with a text, but I'll do something right here on the whiteboard for you. So here we go. Velocity per time, equals meters per second, which is equal to acceleration. And we were originally talking about weight. I got kind of not really off topic, but I get a little excited and start going on tangents. So weight is a force. Weight is a force. So we established that force equals newtons, which equals mass times acceleration. So mass is kilograms. Again, we're getting back to those. Meter, kilogram, second. M, kg, and s. So we're going to go with kg. And then that is kg times acceleration, which is meters per second squared. So we see that weight is actually a force, and is therefore mass times acceleration, which equals newtons, which equals the weight of something. So we see that's why weight is not a fundamental unit. You're not going to weigh the same on the moon as you do here on Earth. But you will weigh the same in relation to anyone else that you would be weighed against on Earth. So if you were lighter or heavier than that person, you would be obviously lighter or weighter by a factor of the change in gravity. So it would stay the same. It would be a locked ratio. So we've talked about derived units. We've talked about fundamental units. One more that we can talk about real quick. We can talk about, like, say, density. So it's going to use a Greek symbol again. We're going to call this one rho. Let's go ahead and edit clear. Let's do a different color here. It's a little more visible. So rho is equal to mass per volume. Mass per volume. Okay, this is just another example of a derived unit of measure. So, meters, kilograms, seconds. So we need to figure out where our fact family comes together here. So mass is kilograms divided by volume. Volume is a space in 3 dimensions, right? It's a measure of 3-dimensional space, right? That's a really ugly cube, but pretend that's a cube. And so that would be length cubed, right? So it'd be meters cubed, right? So that's it. Or centimeters cubed, depending on what our unit of measure is. So rho, rho equals, which is density, equals mass per volume. So kilograms per cubic meter. So what that talks about is something, you might say, well, that's similar to weight. Yeah, it's very closely related to weight, because what it is mass per volume is density. Density says, how many atoms did we pack into your volume? So if this is a person, right, and we say this person here, it's a terrible person, give him some big mouse ears, and he's packed in with atoms. He's made up of atoms. So if he's this tall and packed with X atoms, he has X density. But if he's packed in with the same amount of atoms, but he's only this tall, he's a greater density. So if he has X atoms, he's going to have, and here was X density, here he's going to have, let's say, Y density. It's going to be a new amount of density. Same amount of atoms, but smaller volume. It's going to be a greater density. It's going to be, his density is going to be greater than X, isn't it? So it would be Y is greater than X here. If Y represented the density for this guy, and X represented the density for this guy, so we'll say this is N. We'll say this is N. So if he has N atoms in this taller body, and he has N atoms in this shorter body, and these atoms equal a density of X, and these atoms equal a density of Y, Y is going to be a greater density than X, because we're packing more atoms into a smaller 3-dimensional space. And that's what density is. So, again, it's all just really simple and really intuitive. And the more we do problems together, and the more we talk about these things, and see these things kind of put in visual form on the whiteboard and hear how they're explained, the more sense it's going to make. So we're going to talk about something called conversion factors on the next video. We didn't make it to them on this video, but we will on the next video. But you know what? I'm actually going to give you a sneak peek of conversion factors. So conversion factors are going to talk about moving from one unit of measure to another. So let's say, for instance, that we have 65 inches, 65.0 inches, okay? And I put it 65 over 1 because that's the same as 65, because that's 65 divided by 1. But you'll see here in a minute why I do that. So and we want to convert that to centimeters. So this is what we're given. And in blue, we're going to show what we want. We want centimeters. And we're going to put that as the numerator over here. So centimeters, 2.54 centimeters is equal to 1 inch. Okay? And so what we do is we take what we're given, make it the numerator over 1. We then take a value of 1 of said unit that we're given and put it over here as the denominator. We then put the ratio of that unit to what unit we want as the numerator. So the numerator in this case would be 2.54 centimeters. The denominator would be 1 inch. Again, that inch comes from right here. So we're given 65 inches. Okay? So we put 65.0 inches over 1. And then the denominator and then the adjacent factor is the same unit of measure but given the value of 1. And then its ratio in terms of the unit that we want. We then just multiply straight across, and that's going to give us 165 centimeters. That's the gist of how to solve a conversion factor. Now, these conversion factors can get quite long if we have to convert multiple units of measure, and they can get seemingly complicated, but they really don't. They stay exactly like this. This is just a very small version of how they will be. They will be just that easy. So, this is called dimensional analysis or conversion factors. Sorry about that. Factors. It's an O. There we go. That's it. Or dimensional analysis is the way it was taught to me. All right. Sweet.